Eder hails from the South. He's born in Florida, from Dallas, Georgia, up here. And he came here interested really more in engineering, but we were able to pull him more into the sort of pure chemistry angle. Had him in my virtual organic chemistry classes, just like I had Elizabeth. We had a good time, like across the airways. And so Eder joined my research program this year, and my research program is at this point pretty exploratory, right? So we're making stuff and we're seeing what we can do, and it's always a challenge, when you can do anything, how do you make a decision about what to do? And so Eder found a kind of a cool target that looked interesting, that was understudied, and then he made it. And it was, part of this work, I think, is wrestling with the spectroscopy to be able to prove to other people that, yes, I did make it. Yes, it is clean. But I think this is a really, really hard-won knowledge. And I hope it doesn't sound too arbitrary, but this is much like Ezra's work and much like other work that we've had. Like, I think there's room for exploration in science. And so I'm excited about this. Next year, Eder is considering continuing both his chemistry or other training, and perhaps his football career, because he has a little bit of eligibility. One of the latest of a series of standout football player chemistry majors that we're pleased to have here at Lawrence. And so, yeah, I'm really excited to hear his work here. So, cede the floor.
Can you hear me? Is this too loud, too low? Good. Thank you, Stefan. Okay. So once again, I'm Eder Bellegarde, and for my senior capstone, I chose to do my project over 1,2,4 triazolo 4,3A quinoxaline. For a majority of this presentation, I'll be referring to it as Quin. All right, first thing first is the agenda. So I'm going to talk about heterocycles and how they're used in drug development. After that, we're going to move on to Quin and its target compounds. After that, we're going to research. We're going to talk about the goals that I had and the methods I used to get to those goals and the data I collected from all that. And then we're going to talk about the advantages of Quin, so the modifications. And then lastly, we're going to close off with the discussion and talk about the conclusion and the future research that holds for Quin. All right, so behind me, we have a picture of heterocycles. And heterocycles are used in a lot of drugs. They're predominantly used in pharmaceutical, agrochemical, and veterinary products. Some drugs that have heterocycles are caffeine and morphine. And I know a lot of you guys like to drink coffee, Mountain Dew. So these are compounds that we kind of interact with every day. The compound I chose was quinoxaline. All right, so right here is a table, and basically the table states that more than 86% of medication endorsed during the past 8 years have all been made of heterocycles. And if you look at 2011, you kind of see as we start to go down and progress, there are more heterocycles being used. And that's kind of sort of why I chose to pick this, because it's very beneficial for humans. So expectations of Quin or heterocycles. Well, heterocycles help the body, and depending on the type of heterocyclic compound used, kind of determines what effects it has on the body. Up next is its importance and expensiveness. So heterocyclic compounds are included in beneficial drugs that help fight off viruses and infections, as well as other drugs. So that includes Recrystallization 4, which is kind of seen in Shatnicks, and this is a product that people use if they are quitting smoking and they have that need, that urge to smoke. They take this and it kind of helps ease that down. Another product is bromidine 5, and that's used in eye drops. So when your eyes get really irritated or they get red or even sore, you take this. After that, we have quinoxaline 6, and this is more of a drug you'd see at the hospital. I don't think you can find it at your local Walmart or Target or CVS. It's an antibacterial drug, so it kind of helps with drug resistance and helping fight bacterial enzymes. Lastly is XK469 NSC7, and I couldn't find any pictures of that, but it has to do with supercoiling, and supercoiling basically is when your DNA won't replicate, and we kind of need that to survive. So lipophilicity, it's the ability of a chemical compound to dissolve in fats, oils, lipids, and nonpolar solvents such as hexane and toluene. And you might ask, why is that important? Well, when you take these compounds, you need them to be able to digest and go to the bloodstream and then go to the brain. If that can't happen, then you're kind of just taking them just to take them with no beneficial effect. Up next is, what do you know about our compound? So what we want to know is, what do you want to make, first of all? So the life of Quin. So heterocycles are being used and modified to carry out desired purposes, but not only in the medicinal realm, also the agrochemical and the veterinary realm. So, keep your furry friends alive and in good health. Predominantly majority of this compound is made out of carbons, and carbons are a fundamental block necessary for protein shapes, sugars, fats, and it also assumes a vital part in controlling the normal functions of the body. Like Stefan had mentioned, you could type in this formula, but you will not find a compound like this. So this is rare. The quinoxaline subordinates are valuable mixtures on the kind of their different therapeutic and modern application. Quin is simple, it's inexpensive, and it's environmentally friendly. With that being said, you don't really have to have a PhD to do this. You follow the steps and you get Quin. Compared to other compounds, its simplicity and versatility is what makes it a resourceful and marvelous compound to synthesize with other elements, which calls for its rise in popularity in the medicinal realm. Its age is a major factor on why I chose this. So why Quin? So it's a newly arrived compound, undiscoverable realm, a variety of biological activities, and its beneficial is environmentally friendly, drug adaptation, simplicity, and prevention. So to reiterate, quinoxaline not only plays an important role in organic reactions, but also a wide spectrum of interesting biological activities, which include antibacterial, antiviral, anti-cancer, anti-inflammatory, and antiprotozoal activity. There's not much known about this compound, so further investigation of its selectivity and reactivity is needed to bridge gaps that we have yet to solve. So who knows? This could be, the next drug that can help fight cancer, HIV. Possibilities are endless. So how can we change Quin? So we can change Quin with using alternative methods, and that is just to modify our quinoxaline heterocycle to observe its reactivity. Some forms of alternative methods include photochemistry, flash chemistry, and flash chromatography and molecular modification. Modifying our quinoxaline heterocycle to observe reactivity. To do so, we have to consider a few steps. Primarily, the first step is, can we make it? What do we know about it? And why do we care? After that is seeing its reactivity and selectivity when it is reacted with certain elements. And all these circles here represent places we can, put different elements. So we could put a methyl here, 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 and here. All right. So we know what we want to make. Now, how do we make it? So we want to understand Quin to make a better and stronger compound. So it's time for development. All right. So this is a full synthesis. It's a 3-part synthesis. So the first synthesis, we begin with the synthesis of having dionyl chloride react with 2-hydroxynoquinoxylane to give us this 2-chloroquinoxylane. So it's a very simple reaction. The hydroxy basically bonds with this. It makes a 5-bond system. The chlorine gets kicked out to stabilize this. After that, the chlorine gets back in because it is a nucleophile and it attacks this carbon because it is the most positively charged carbon out of all of them. Then the electron moves upwards into the nitrogen and it becomes unstable because it wants to have 3 bonds. So it goes back in there, and we end up losing this compound here, and we get stuck with our chlorine. All right, synthesis 2. So now this is where the 2-chloroquinoxylane we just made is reacted with a hydrazine hydrate with H2O to give us 2-hydroxynoquinoxylane. And this is a simple reaction as well. This is a nucleophilic aromatic substitution enabled by electronegative nitrogen. So it attacks here. Electron gets pushed up into nitrogen, unstable, goes back down, and it kicks out chlorine because it's a good leaving group, and because it's nucleophilic. All right, and then the last one is a little bit more difficult to explain, but I think I got this. So the 2-hydroxynoquinoxylane reacts with the triethyl orthoformate to give us the 1,2,4 triazolo 4,3 quinoxylane, otherwise known as Quin. So acid makes this triethyl orthoformate in the electrophile. Our lone pairs react with the carbon, and the last 3 steps are kind of the same thing. So what's going on here is we're losing our ethyl, and this kind of just keeps on going until we're all out of ethyl and we're left with the hydrogen here. So end goal, 2-hydroxyquinoxylane to Quin. All right. So we know we want to make. We know how to make it. Now the question that lies ahead is, did we actually make it or did we waste time? And if we did make it, how do we know? So to confirm this, we use some methods such as TLC, Gcms, and NMR. So TLC can be used to determine the number of components in a mixture, and it identifies the compounds. So right here we have 3 compounds. This one right here is the hydroxy. This is the hydrazine, and this is the Quin. And if you just look, you see that they're not the same structures at all, which means that we actually did form a different compound and we didn't just waste time. All right, so NMR, that stands for nuclear magnetic resonance. So the external magnetic field changes the resonance frequency, thus spitting out an electronic structure of a molecule in its individual functional groups. This technique is used to observe local magnetic fields around atomic nuclei, and it has a high accuracy rate. So I'm about to break this down and explain to you guys this NMR. I'm going to do it in 2D and then do it in 3D. So how do we know we actually made Quin? Well, we have these singlets here, and they correspond with these hydrogens here. And we know that because of how far they are from each other, and because these are the most reactive hydrogens in this entire compound. After that, we have our C and D, and we know that it's C and D because this doublet is kind of far, but it's not far and it's not large like the singlet. And then this multiplet, it stands for E and F, and we know that it's going to be next, or it's not next, it's going to be neighbors to D, and if it's neighbors to D, it's most likely to be a neighbor to C as well. So that's how we know it's there. All right, on to the 3D. So this is how we really know. So we have this dark spot right here, and that corresponds to the A and B. So there's nothing around it, there's nothing affecting it, it's solo dolo just hanging out by itself. As we move in, we go to our doublet. So we have D, and we know that D is next to E because of how close it is and the dot that forms here. We also know that it's close to C is close to F because this is or not this dot right here represents C, and we see it here once, and it's on the outside, and if you draw a vertical line, it connects straight to C. So up next is GCMS. It's a very complex. A complex sample is separated by GC, which produces various peaks in the gas chromatography, and each peak generates a unique mass spectrum used for compound identification. So GC, the compound is injected into the GC, it's heated up, and it's ran through this little wire, I believe, and it's ran multiple times, until it's broken down, and the compound mixture is then detected, and it's telling us to see if we actually have a high presence or a low presence of our compound. And this is a really beautiful peak, so we know we actually have something, and something was actually made, and it's not just, a distraction, I believe. So going from there, we have our mass spec. This measures the mass of the charge relation of one or more molecules presented in the sample. The measurement is issued to calculate the exact molecular weight of the sample component as well. If we break this down, we get C9, H6, N4. And what that basically means is the molecular weights. And when you combine all of them together, you get 170. So we want to see a peak at 170, which we see here, and that's how we know we have it. These other peaks, 143, 116, that's kind of happen when you split this in half right here. You get 143 and 116. Pretty sure you got to split this guy here in half, and you get 116. So what do you want to know about our compound? We know what we want to make. We now know how to make it. We know that we did make it, and we know how we made it. So what information do we have on this type of molecular structure? Well, we know it's a promising compound. We know it's stable, environmentally friendly, and simple, and it has the potential to be an antiviral and antibacterial agent. So what I learned that hydroxylic compounds are utilized in many drugs. And I understand why and what leads to hydroxylic compounds being manipulated. And I understand how we can manipulate them in order to perform functions that we need to survive as a community. So modifying Quin. There are various ways you can modify Quin, and that includes Menasee reactions, radical reactions, photochemistry, molecular modification, flash chemistry, and green chemistry. So right here, this is one of the ways we attempted to modify Quin. And it's basically this simple and clean photoinduced methylation of heterines with methyl. It requires a photochemistry technique, and it took about 3 weeks. Realistically, that can be done a little quicker. In the end of the experiment, we didn't fail, but we didn't succeed, and that's kind of because of timing. There were other things I had to deal with. I'm a college student, so I have other priorities I have to worry about. But further research would involve making knowledgeable chemical modifications to Quin, and now that I understand it, I know we can definitely make it, and we can definitely modify it, but that all depends on time. And this is what we tried to do. So we tried to put a methyl group here and a methyl group here. Sadly, because of time, we couldn't do so. We did realize that a day is too long because our product would start to decompose, and an hour is too short because our product wouldn't form. But I think the sweet spot may be 4 to 5 hours. So if someone would continue this work, they most likely will modify Quin and form these methyls here or here, depending on how they go about it. How long did it take, and why is that important? So it took me 3 terms, but like I already mentioned, it can be done in 3 days, the entire, from the hydroxy to the Quin. And that's important for pricing and production, making a lot of this product and shipping it out. All right. Why is time important, and does it lead to a higher yield? So time is important because it affects how much product we can make, and it also means less or more room for error. And we do know that it does affect yield directly. So the longer the experiments, the more mistakes that could potentially happen. Supervision can possibly lead to reactants getting formed or getting lost in the air, unwanted products forming, or even the reaction just stopping and impurities forming. And we also learned that if it's too short, that can do the same. It might have a sweet spot, and we can miss it maybe by a couple of seconds or a couple of milliseconds if we're not careful. So, agenda. We talked about heterocycles and we talked about drug development. Oh, never mind then. Sorry about that. This is a recrystallization of the hydroxynoquinoxylane that I found really interesting. If you look closely, you'll start to see that the compound forms this cloudy looking thing. So if you start to see right there, you see it start to become cloudy. It goes from this light brown to this lighter orangish color. And that's all I have for that guy. Here are my references. Next is my acknowledgments. I want to thank Professor Deanna for, pushing me to become a chemist. I had the option to do other things, but she told me that this would possibly be a great career and that I could possibly succeed. And I believed her and I followed the steps she set. And everything's been cool ever since then. I want to thank Dr. Debert for allowing me to join his research team. He's a busy man, and even so, he said it was cool and helped me and guided me even when things weren't going the correct way. He let me know that, hey, that's part of chemistry. You got to fail before you can succeed. I want to thank Professor Sazama. Me and him talked a couple of times, and he really mentioned how to attack presentations and what to do and how to remain calm. I want to thank Dr. Dowdy for keeping me accountable, even though I was slacking a little bit. I want to thank DMART for providing the glassware and all the products that I use. Evelyn for dragging me down here at around 12 o'clock to present this and practice, and the rest of my Chem 680 colleagues. Thank you.
Thanks, Eder. Eder is now ready to take questions from the floor. Yes, back there.
Do I have to scream or are there microphones?
I can hear you on the
Okay.
microphone.
I
You
don't
are
know
good
this
to talk in a normal voice.
Okay, thank you. I don't know chemistry. How do you modify a compound?
How do you modify a compound? All right, so give me a second. So modifying a compound isn't as complicated as it sounds. So, for example, here we modified this hydroxy group. You kind of just find your reactants, and you set up your procedure. You set up how you want to go about it. So whether you want to do it heated or you want to be cooled, and you work out the synthesis to make sure that it'll work and to make sure that you're actually knowing what you're about to form.
How do you find stuff like that? How do you find recipes and get ideas?
Well, chemistry is a very amazing thing, and because of it, a lot of us like to share our information and like to share our work. So others provide what they've done, and you can kind of build off of that and use your own way. So it's kind of like cooking. Like there's a set recipe, but you can, do your own thing and also follow the recipe and make something beautiful.
Thank you.
Very deep. Allison?
So synthesis is awesome. It terrifies me. But also for the reason that you always run into obstacles and it doesn't quite work out the way that you hoped it would, as you mentioned many times. Can you tell me one time that it actually did work out, and like that you went in and you're like, okay, I'm gonna get this one step, and it was successful and you got exactly what you were expecting?
This step right here, honestly, was the get-go of everything. We wanted to put this chlorine here, and it worked the first time around. It had a very high yield. Don't quote me, but I think it was like a 75 to 80 range yield. So it was meant to work.
Cool.
Elizabeth.
So you had mentioned a little bit with like after getting your compound and doing modifications that it was denaturing after like by 24 hours. What is that? Does that like I really signify anything about the molecule? Is it still like super stable, like with it being a triazole, or what does that mean exactly?
I'm so sorry. Can you repeat that question?
For sure. So you mentioned that with the modifications that it was denaturing after about like by 24 hours, and so these triazoles are very stable. Like, what does that tell us about this molecule? Is it still like a great target, or like what should these next steps be doing?
That's a good question. So going back to the decomposition, I think that was just, it was just cooking for too long. So like, going back to the food analogies, because I've always been told chemistry is like baking. If you know how to bake, you know how to do chemistry. But it kind of just cooks too long, it's heated for too long, and the products, they form. But after a certain amount of time in the photochemical reactor, it does too much, and it just ruins the entire product. So it's overheated, basically.
And that photochemical reactor is a big, scary beast. So it's much more powerful than an oven. Other questions for Eder? Evelyn.
So you mentioned that the reaction is environmental friendly. What makes this reaction environmental friendly?
So going back to this guy here. So right here we have hydroxynohydrate, and it's very toxic to humans. But once it's exposed to oxygen, all that kind of goes out the door. So we can actually, react it with the quinoxaline, as well as another reason why it's environmentally friendly is the photochemical machine. It's not harmful to the environment. It allows our process to go at a much quicker rate than if we decided to, heat it over a stovetop or in the oven.
All right, any other questions for Eder? If not, let's thank our speaker again. Join us next week for the last week of chemistry senior seminars, Tuesday, Wednesday, and Friday. We'll see you all then.